So question number 1 was asking us to describe how a pure sample of chlorine can be prepared in the laboratory from potassium manganate crystals. Your answers should include a well-labeled diagram and equation for the reaction. What I can say here is many of you forgot what I told you. Please, a gas cannot be pure when it contains water. A gas cannot be pure when it is not dry. So I want you to run this from today. Times change, the questions have changed. We shall not ask you to prepare a gas which is not dry. That is going to be very rare. So whether we have told you or not, prepare a dry gas. You should always prepare a dry gas. So, for example here, describe how a pure sample of chlorine can be prepared in the laboratory from potassium permanganate. We had to use potassium permanganate and concentrated hydrochloric acid. However, I was somehow disappointed with your friends who decided to use manganese 4 oxide. The question is clear. It has said that you use potassium manganate 7. So if you don't know how to use potassium permanganate to prepare chlorine, then it is better you don't do that part of the question, because you are going to get, all you are going to get is 0. If the question says use potassium permanganate, then you should use potassium permanganate. Again, method of correction, many of you collected the gas over water. You collected the gas over water, and that is not what I wanted. Because chlorine gas dissolves in water, forming hydrochloric acid and hypochlorous acid. So if you collect it over water, then it will react with the water. So I wanted you to collect the gas, and I wanted you to dry the gas first, and then you collect it by downward delivery. I tried it. I drew the diagram, and this is what I came up with. The only difference, I told you, I don't know, I talked about that very many times. The only difference when you use manganese 4 oxide is that for manganese 4 oxide you heat, whereas for potassium manganate you don't do what? You don't heat. For potassium manganate 7, there is no need for heating. The reaction takes place at room temperature. So this was our diagram. This is our funnel, and in the funnel we put concentrated hydrochloric acid because it is a liquid. Then in the flask, this should be potassium permanganate or potassium manganate 7, although I forgot to label it somehow, but that is our preparation flask. Then when hydrochloric acid concentrated gets to potassium manganate 7, a colorless gas, no, not a colorless gas, a greenish yellow gas is given out, which is chlorine. And that greenish yellow gas is first bubbled through water. Ensure that your flasks your flask and wash bottles are corked properly. For those of you who don't know what I mean by to cork, there are these shaded lines, these ones. That means you have corked the flask such that the gas cannot escape to the atmosphere. Eh? So this is water. What is the role of water? Someone tell me what is the role of water there? Hmm.
To remove hydrogen chloride.
Very good. To remove hydrogen chloride fumes. Eh? Yes, to remove hydrogen chloride fumes. And this is concentrated. What a mistake. Don't know how I made this mistake. This is concentrated sulfuric acid. Please note that this is concentrated sulfuric acid. Hydrochloric acid is not a drying agent. This is concentrated sulfuric acid to dry the gas. And finally, chlorine is prepared by downward delivery. So most of you drew the diagram well, and I was happy with that. But remember, the question was describe. When they say describe, you don't stop at the diagram. After drawing the diagram, you write some words to talk about your diagram. Now, when I'm marking, remember the question had said describe how chlorine, a pure sample of chlorine can be prepared from potassium permanganate or potassium manganate 7. Now, potassium manganate 7 was given to you in the question. So that one I will not award you my mark because it was already given to you. But hydrochloric acid was not given, so I will give you a mark. So concentrated hydrochloric acid is added through a Fiesel funnel to potassium permanganate in a flask. Remember, if the question was explained, then you would have given a reason why concentrated hydrochloric acid is added through a Fiesel funnel. And the answer is because it is a liquid. Potassium permanganate in a flask because it is a solid. The gas produced is passed through a wash bottle containing water, and the role of water is to remove acid spray or to remove hydrogen chloride fumes. The gas is then passed through a wash bottle containing concentrated sulfuric acid. We said this should be concentrated sulfuric acid and not hydrochloric. We shall correct that when we are doing corrections. Concentrated sulfuric acid for drying. And finally, the gas is collected by downward delivery since it is denser than air. When they say describe, I told you, whether they have told you to write the equation or not, you know there will always be 1.5 marks for the equation. When they say describe, when they say explain, 1.5 marks for the equation will always be there. And this is our equation, which you wrote very well. But some of you, the way you took pictures, I was not able to see the last part of chlorine, so I denied you the mark. And some of you were writing Cl and forgetting that chlorine is diatomic. You are forgetting to put these two, so you also lost the mark. So I told you to always remember that when you are balancing this equation, there is 16 on hydrochloric acid. There is 16 on hydrochloric acid, and when you put 16 on hydrochloric acid, then you must put 8 on water to balance what? Hydrogen, to make it 16. When you put 8 on water, then oxygen will have become 8, and these ones are 4 on potassium permanganate. So you put 2 to balance oxygen, and when you put 2, then you must put 2 on potassium chloride, and 2 on manganese 2 chloride. This is the formula for manganese 2 chloride. Most of you are forgetting the 2, and therefore you lost the marks. You are forgetting the 2 on manganese chloride and the 2 on chlorine. So that was it for number 1 part A. Anyone having a question on number 1 part A? I want to go slowly so that you understand this work. Any question? Okay, let's proceed. B, part 1. State what would be observed if chlorine was bubbled through a blue litmus solution. So there is no difference between a blue litmus paper and a blue litmus solution. So a blue litmus solution, when chlorine is bubbled through, who can tell me the answer? Let us contribute. Let's move together. Who can tell me the answer there? Just unmute and tell us. You passed that thing. Can you tell us what is observed when chlorine is bubbled through a blue litmus solution?
The solution will first turn red and then finally colorless.
Good. The solution would first turn to red and finally colorless. Why does it turn to red? It turns to red due to formation, because a solution, since it is a solution, it means chlorine will react with water to form hydrochloric acid and hypochlorous acid. So the hydrochloric acid will turn the blue litmus solution to red, and hypochlorous acid, which is a bleaching agent, will turn the red litmus solution to colorless. So that was the answer there for that part. The blue solution turns to red and then to colorless. Now here we are saying when chlorine is bubbled through a solution of potassium bromide, what will be observed? I first ask, what is the color of potassium bromide? Please, let's
Red.
go first. Okay?
It's a red solution.
Potassium bromide, no. It's not red.
Okay. Colorless.
Kathy?
Colorless.
Good. Potassium bromide is colorless. So what happens? I want you to get your pen and we write this. What happens when chlorine is bubbled through a solution of potassium bromide? We had seen this in our notes, and we said the colorless solution turns to red or reddish brown. The colorless solution turns to red, or you have to give one of those answers, but here let's say the colorless solution turns to red. Colorless solution turns to red. Then we said you can be asked to explain that, and the explanation was the explanation was chlorine is more reactive than bromine. Don't mix. When you are using chlorine, use chlorine and don't mix with bromide ions. When you are using chlorine, it goes with bromine. Don't mix with bromide what? Ions. So we say, please, I said we write this. chlorine is more reactive than bromine. Therefore, chlorine displaces bromine. Therefore, chlorine displaces bromine from its solution. Therefore, chlorine displaces bromine from its solution of potassium bromide. Chlorine displaces bromine from its solution of potassium bromide, forming bromine, which is red. Forming bromine, which is red. Now that is one version. That is one version. Now, if someone wants to use bromide ions, we'll say that chlorine oxidizes bromide ions to bromine. Chlorine oxidizes bromide ions to bromine. That is if you want to use bromide ions. But I urge you to go with the first explanation. It will not confuse you. Chlorine is more reactive than bromine, or someone could say chlorine is higher than bromine in reactivity series. Chlorine is more reactive than bromine, and therefore chlorine displaces bromine from its solution of potassium bromide, forming bromine, which is red. So the observation there was that a colorless solution, which is potassium bromide, turns to red. And I'm saying I allowed those who wrote reddish brown. Let us look at the equation right away also, because it was part C. The equation is here. This is potassium bromide plus chlorine, and we have been telling you that chlorine will displace bromine from its solution of potassium bromide, and it will form potassium chloride and what? Bromine. And bromine gas, or liquid. The states are two here. We can have bromine gas or bromine liquid. But let's take liquid. Here I'm showing you that I allowed those who had two versions. I don't know how I forgot to put states here. The state is aqueous for potassium bromide, and the state is aqueous for potassium chloride. Many of you forgot to balance. You should have balanced by putting 2 on potassium bromide and 2 on potassium chloride. Then the other question was, chlorine was bubbled through a solution of iron 2 chloride. What is observed? Iron 2 chloride solution, we said, what is the color of iron 2 chloride? Who can tell us? Beza, what is the color of iron 2 chloride? What did we say is the characteristic color of iron 2 compounds? Someone tell us, please. Iron 2 compounds, we said they are green. So the answer here, when chlorine is bubbled through iron 2 chloride, The answer is a green solution turns to yellow. Why does it turn to yellow? It is due to formation of iron 3 chloride, which is yellow, yet iron 2 chloride is green. So the answer here is a green solution turns to a yellow solution. And the property of chlorine here is that it is an oxidizing agent. In part 2 and part 3, chlorine is working as an oxidizing agent. It is using the oxidizing property. Write the equation for the reaction between B2 and B3. For B2 we have already seen. B2 we have already seen, that is potassium bromide, which is colorless, plus chlorine, forming potassium chloride, which is still colorless, plus bromine liquid, which is red. Then for part 3, we wrote this equation, remember, iron 2 chloride plus chlorine, it will form iron 3. Iron 2 chloride plus chlorine will form iron 3 chloride. So iron 3 chloride means iron is using the valence of 3. And that's why, and chlorine uses a valence of 1. That's why iron 3 chloride is like this. And iron 2 means chlorine is using a valence of 2. So that is our iron 2 what? Chloride. To balance, this one, chlorine atoms, they are 4 on the left hand side and they are 3 on the right hand side. So put a 2 to make them 6, and that's what you get. Then there was a question, part D, it was telling you, I hope you have your question is there. Write an equation between chlorine and iron. The product when chlorine is passed over heated iron wire, the product is iron 3 chloride. Please note that the product there is iron 3 chloride and not iron 2. Iron 2 chloride is formed when hydrogen chloride is the one that is passed over chlorine. Chlorine forms iron 3 chloride. Then hydrogen chloride forms iron 2 chloride. All those equations, we looked at them. And if they ask you for the observation, this is the iron grows red hot and it forms black crystals, black solid. The black solid is iron 3 chloride. Then chlorine with sodium hydroxide, dilute sodium hydroxide. We saw that very many times. The product is sodium chloride plus sodium hypochlorite. And sodium hypochlorite is a pale yellow solution. Remember, in all these cases, we could have asked you for the observation. So for sodium hydroxide with chlorine, a pale yellow solution is formed, which is sodium hypochlorite. And for chlorine with iron, we form iron 3 chloride, which is black solid, and we balance. And we do what? We balance like that. But what is important for you to note is to avoid this confusion. Chlorine with iron, pure iron metal, you form iron 3 chloride. And chlorine with hydrogen chloride, no, hydrogen chloride with iron to form iron 2 chloride plus hydrogen. Hydrogen chloride plus iron, the product is iron 2 chloride plus hydrogen gas. Then chlorine with iron, the product is iron-free chloride. This chemistry is very important and very common. We are going to number 2. Number 2 was very simple and short question. Nitrogen, you can be writing down the corrections, eh? No, the important parts, eh? After the lesson, I will send you corrections after all. Nitrogen can react with hydrogen in presence of a catalyst, which is finally divided to form ammonia in Haber process. State the source of nitrogen. Nitrogen, the source is atmospheric air. The source of nitrogen is atmospheric air. The most important part there is air. Many of you are saying fractional distillation of liquid air. That is all correct. Everything is correct, as long as the word air is there. So nitrogen comes from air. Name the catalyst used in the reaction. The catalyst is iron. They have already told you that it is finely divided, so there is no need of you to say it is finely divided iron. No. Name the catalyst, and for a half mark, just put there iron as the answer. Explain why the catalyst is finely divided. The catalyst is finely divided to increase on the surface area, to increase the surface area for the reaction, so that nitrogen and hydrogen can react fully. We want all the nitrogen and hydrogen to react. That's why we divide the iron. That's why we use finely divided iron, to allow all the nitrogen and hydrogen to react fully. Then part 4 was asking for the equation. Most of you wrote the laboratory preparation equation. You had calcium hydroxide plus ammonium chloride. That one is wrong. I crossed it. That was laboratory preparation. The question was clear. It was saying Haber process. The question was clear. It was saying Haber process. Finally divided in the Haber process. So in the Haber process is the direct combination of nitrogen and hydrogen to form ammonia. So the equation we were interested in was this: ammonia, nitrogen plus hydrogen forming ammonia. And some of you forgot to balance. These are 2 nitrogen atoms, so put 2 on ammonia, and when you put 2, hydrogen becomes 6, so you also put 3 on hydrogen. Was writing plus heat necessary? That is not necessary. With or without it, you get the mark. You don't have to add plus heat. That one is not necessary. Whether you put or not put, you'll get the mark. Now, one condition, we have already seen it, which is catalyst, and the catalyst is iron. Condition for this reaction, they were saying you give other conditions for this reaction to take place. The other condition is pressure, and the other condition is temperature. If the question had said the conditions for maximum yield of ammonia, you remember this reaction is reversible. A reversible reaction is the one where both the forward reaction and backward reaction are taking place. So the forward reaction is the one which is formation of ammonia, and the backward reaction is the one which is formation of nitrogen and hydrogen. If they wanted equation for conditions for maximum yield of ammonia, then we would have to say high pressure of 200 to, is it 500 atmospheres, and low temperatures of 450 to 500 degrees centigrade. But since they just said conditions, they didn't specify, we just put pressure and temperature. Then there was a question saying, write an equation to show that ammonia can act as a reducing agent. This was the best equation for you to write. Many of you wrote very fake equations. Ammonia, yes, ammonia can work as a reducing agent. This was the best equation for us to write because we saw this. So ammonia plus copper 2 oxide, the product is copper. That means ammonia has clearly reduced copper 2 oxide to form copper. And itself has been oxidized to nitrogen. Remember this equation I told you when you are balancing, you remember that there is 3 on copper 2 oxide and 3 on copper. Then the rest will come. You put 3 on water to balance oxygen, then everything will balance. Alternatively, this is nitrogen gas and there are 2 atoms. So begin by putting 2 on nitrogen and hydrogen will become 6. When hydrogen becomes 6, put 3 on water to balance hydrogen. And oxygen is become 3, so you put 3 here and 3 there. Then the second equation was asking you to write an equation between ammonia burning in oxygen. They didn't tell you about the catalyst. So this was the equation, not the other one, which forms. Remember, we agreed that when there is no catalyst, the product is nitrogen and water. But in presence of a catalyst, the product is nitrogen monoxide. So in absence of a catalyst, the product is nitrogen. And I told you this equation is not easy to balance. So put 6 on water, and the rest will balance itself. Put 6 on water and hydrogen is become 12, so you put 4 on ammonia. When you put 4, you have to put 2 on nitrogen. Then the other equation was write equation to show burn in oxygen. This one we have finished it. Ammonia obtained by the Haber process can be converted to nitrogen 2 oxide. Nitrogen 2 oxide means nitrogen is using a valence of 2, and oxygen also has a valence of 2. So the compound is NO, which is nitrogen monoxide. And the equation was this. Ammonia plus oxygen, you get nitrogen monoxide. But this takes place in presence of a catalyst, and that the question was asking for the conditions for nitrogen monoxide to be formed. One of the conditions is a catalyst. And don't just say catalyst. Next time I will cross it, you just say addition of platinum as a catalyst. Mention the catalyst. And the other condition is you must heat. Then lastly, part D was asking you to write equations to show how this nitrogen monoxide formed can be converted to nitric acid. And it was 3 marks. There, we wanted only 2 equations. Don't again start from this one of formation of nitrogen monoxide. Now, some of you, when you form nitrogen monoxide, you write another equation where nitrogen monoxide goes to nitrogen dioxide on the same space. No, on the same part. If the question is asking you to write an equation for the formation of nitrogen monoxide, why do you include nitrogen, the formation of nitrogen dioxide in the process? You don't have to go there. So equation is to show how nitrogen monoxide can be converted to nitric acid. There are those two. We have seen them many times and they don't change. So they still remain the way they are. They still remain the way they are. So that was it for the test. I now invite you to ask some questions if they are there. Any question? Any question? If there is no question, I'm sending you the corrections and I wish you a good day. God bless you. I'm going to send you the corrections so that you can go through further.